Hello everyone, I hope all of you are ready to start linear programming problem for your forthcoming board examinations, where I'll explain what you need to do step by step. Whatever I'll be discussing here, that is included in your syllabus, those who are in applied mathematics. For mathematics, those who are appearing for 2025 linear programming problem, they don't have to solve any practical problem. I mean, solution where problem based solution they don't have to do. Okay, rest of it, whatever I'll discuss, it is there in your syllabus, but I will be discussing the general concept of linear programming problem now. Okay, which will help the students of both the streams. In general, LPP means linear programming problem. Programming means what? Meaning, in general, programming in this context refers to the process of planning or scheduling activities to achieve a specific goal. In linear programming, this programming involves creating a mathematical model to optimize a particular objective, like maximizing profit or minimizing cost, subject to certain constraints. Essentially, it's about finding the best way to allocate limited resources. Some of you are just after finishing your all the degrees, professional degrees, whatever, going to set up a factory, business, whatever. You have some limited resource. You have to get the maximum profit based on the resource. Similarly, at the same time, you have to minimize the cost. So your problem is to find the best way to allocate limited resources. If you want to know a mathematical method of minimizing your cost or maximizing your profit, the linear programming problem, or in brief LPP, which is included in your syllabus, is your best help. Okay, so why it is called programming, I hope I have explained. Process, it is the process of planning or scheduling activities to achieve a specific goal. What is your goal? To minimize the cost and to maximize the profit. But this subject, believe me, was not invented because of this purpose. In the Second World War or World War II, this subject was developed by one of the power, I mean superpower. On that side, there was US, England, they were involved. They appointed physicists, mathematicians, engineers to devise a method which will help to know, to estimate about opponent's policy and to find the best way to dominate the opponent. This was the origin of the subject, Second World War II, and that is in the battlefield. Mathematics was being used in battlefield that time. But nowadays, this is a very important part included in applied mathematics. Not only here, there are various branches of mathematics, higher mathematics, where you can apply the concept. Queuing theory, one of them, you can make investigation over there. And this problem itself at your level, that linear programming problem, to solve it is very interesting, and you can imagine how mathematics can be used in our daily life solving problems. Okay? Then programming meaning I told you. Why it is called linear, that also you have to know. Linear refers to something that is straight or follows a straight line. That is called linear. In linear programming problem, how does it arise? Actually, in linear programming problem, we find the relationship between the variables in the model and linear. Those are all linear. This implies that objective function and the constants are linear equations or inequations. One thing I'd like to say, we are discussing linear programming. Is it possible to have quadratic programming? Yes, it is there in higher mathematics. It is a part of operations research. Quadratic programming is also there. But the simplest form of programming, which is most useful in a daily life, where variables have linear relationship. Those relationships will be like this: 3x plus 2y equal to 5. Two variables x and y are related that manner. You understand? Now automatically you will ask a question, why all these variables? I just give you some idea. When you are going to manufacture something in your factory, it depends on different types of raw materials. It depends on their cost. It depends on the number of units you are producing. When you assume that one type of material which you produce, it has some number you are willing to manufacture, another type that also you are willing to manufacture, you replace those things as variables x and y. Then use the given condition to find out the linear relationship like this between them. We do this in linear programming. All the relationships we find, that will be in terms of linear equations in two variables. Okay? So the terms I already told you, that objective function, that is not explained. Let me explain all those terms. Before doing that, I'll just make you familiar once again with the related terminology we are going to apply. This linear programming is a mathematical technique used for optimizing particular quantity. I told you it may be your profit, it may be maximization of your production, and this linear programming problem you will frame. Why? Because of efficient resource allocation. Raw material, time, labor, cost of warehouse, all these things are related. Cost minimization, profit maximization in business model also there. It simplifies decision making for complex problem involving constant. Constant will be there, that definitely I will tell you. Just tell you what is our decision variable over there in linear programming. The variables I already told you, that represent choices or decisions to be made. The number of products to manufacture, those are decision variables. Okay, like x and y. Now, restrictions or limitations usually expressed as linear inequation or equation, those will define some constant. Those will represent graphically some portion of xy plane. That portion will be referred as feasible region. Feasible region basically your solution region, where those decision variables you have taken. I have given the example of decision variable x and y. Those, when represented graphically, they will represent a region that is called feasible region. Objective function, again it's a linear function which you are going to optimize, maximize or minimize. And the technique of finding the maximum or minimum value is called optimization. And remember, those decision variables x and y must be always positive. They can never be a negative quantity. All these things you have to keep in your mind. Okay? Now we are going for mathematical formulation of LPP. I just give you the example first. Just go through this example. A company produces two types of goods, A and B. Each unit of A requires 4 hours of labor, 3 units of raw materials. Each unit of B requires 3 hours of labor and 2 units of raw material. Company has 240 hours of labor and 180 units of raw material available. Profit from A is rupees 6 and from B is rupees 5 per unit. Okay. So what is the problem here? This company produces, assume it's your company, it produces two types of goods, A and B. For A, just if you start listing this manner, for A, this is product A and product B. This is hours of labor available, I am writing here. I am extremely sorry for sudden break here. I just continue the problem. So this linear programming problem I was discussing with you. Hours of labor for A, how much required, that is given. 4 hours of labor for what? A requires. A requires 4 hours of labor, A. That will be taking here. And raw material, 3 units. B requires 3 labor hours and 2 units of raw materials. Then if you write profit, this is your choice. You will write row wise or column wise, it's up to you. Profit per unit is rupees 6 here and this one rupees 5. This is the given problem and you are going to formulate this one as a linear programming problem. You can see that profit is involved, so we are going to maximize the profit and the resource is limited, so we are going to put constant over there. These are the steps you are going to follow when you are going for mathematical formulation of LPP. Identify decision variable. Those are represented by quantities x and y. This is your step 1. Formulate the objective function. Objective function means what? Which you are going to maximize or minimize. Identify constant. Those linear inequations I told you that you have to identify. And the 4th step, write the problem in mathematical terms. It means express the objective function and constants using linear equations or inequations. Okay? So first decision variable you have to decide. Decision variables, as you are going to maximize the profit. Suppose we want to, let us maximize the profit. So what are the decision variables here? That we take as x and y. Let x be the number of units of A and y be the number of units of B. Objective function, maximum profit is z equal to 6x plus 5y. Constant, why 6x plus 5y? You can see that this one is being produced x units, this one y units. Profit per unit of this is x, 6. So net profit will be 6x. From here 5, so profit will be 5y. This is the objective function. Everyone tries to maximize the profit. So we write objective function maximize the profit z equal to 6x plus 5y. What is the constant over there? Because if I just go through this part, it has 240 hours of labor and 180 units of raw material. So I am just adding one more column here, that is availability, AV. Total labor hours available 240 and this one 180. So based on that we can set up two constants. What are those? Just see the availability over there. That constants are what? One is on labor constant. Total labor hours available 240. So if x units of A required, A produced, then labor hours required 4x. This one is 3y. So 4x plus 3y less than equal to 240. And then 3x plus 2y less than equal to 180. Why? Because it is given 180 units of raw material available. For x unit, how much raw material you have used? 3x. And here 2y. That's why you are writing 3x plus 2y less than equal to 180. So objective function part is done. Decision variables you have taken x and y. Then constant, the third part is also done. Fourth part, non-negativity constant, that is x and y, those cannot be produced in a negative manner, I mean negative quantity. So x and y must be greater than equal to 0, that is non-negativity condition or constant. So this is an example of formulation of linear programming problem. I hope you have understood till this. Why linear, that I have explained. Why it is programming, that also explained. And the related terms, three main terms are there: decision variable, objective function and constant. This we can express in the form of matrix also. There may be requirement expressed in the form of matrix. These non-negativity conditions by using matrix 4, 3, 3, 2, x, y, this is less than equal to 240 and 180. Finished. Okay, and xy greater than equal to 0 always, xy positive. So you understand how to formulate. I have explained with the simplest example here. Now what kind of problems we are going to do, I will be explaining here. Different types of linear programming problem. It consists of manufacturing problem, where the objective function is to maximize profit or minimize cost of production by considering the given resource constants. This is manufacturing problem. One type of problem, just one type. You are going to manufacture something. I am just discussing more about the problem, but before that, diet problem. This is the second type of problem we normally meet in linear programming problem. Minimize the cost of diet while ensuring all nutritional requirements are met. That is diet problem. Transportation problem. This is a very interesting problem for students of applied mathematics. Very important, very interesting. It has a daily life application. Don't say that these two don't have daily life application. All manufacturing problem, diet problem, they all have daily life applications, isn't it? Can't say that manufacturing problem don't have daily life application. Like a brick manufacturer has two depots A and B with stocks of 30,000 and 20,000 bricks respectively. He receives order from three builders PQR for this and this bricks. Cost in rupees for 1,000 bricks to the builders in the form of depot. Builders from the depots are given this way. It's like this, from to. From A to P, this is the cost. From A to Q, this is the cost. From A to R, this is the cost. From B to P. The question arises in this manner: how should the manufacturer fulfill the orders so as to keep the cost of transportation minimum and formulate the above problem as a linear programming problem? This we have to do. I am coming back to this problem. Definitely we will solve, but no diet problem. See the example. Person needs at least 80 gram of protein, 100 gram of carbs per day. Food A provides 10 gram of protein, 20 gram of carbs per unit. Food B provides 20 gram of protein, 10 gram of carbs per unit. Goal is to minimize cost of food while meeting nutritional requirement. Give the cost of each unit A. Given this is rupees 60 per unit, and this one rupees 40 per unit. The way I did previous one, we'll formulate, we'll find the best solution. Another transportation problem, this I am not discussing now because already I told you. Now, based on those information, based on those problems, we have to answer following questions. That for transportation problem, formulate the objective function constant of the above linear programming problem. How many units should be transported from each factory to each depot in order that transportation cost minimum? But this will be our step, one of the steps in solving problems. Before that, let me tell you two different methods of solving linear programming problem in two variables. One method is corner point method. What we will do there? See, I have written all the steps one by one. I will be sharing the note also with you. What you have to do there? Plot the inequalities as straight lines of graph on a graph. And these are the steps. Already I have explained. Constant. Graph the constant. Second, find the feasible region. When you graph the constant, automatically feasible region will be there. Identify the corner point. evaluate the objective function. All these terms are familiar to you now. Then find the optimal solution. This we haven't done. Once you do the feasible region, optimal solution is obtained one of the corner point. That's why this step, fourth step is there. Calculate the value of the objective function at each corner point. After plotting the region, you will get a convex polyhedron type diagram. It has many or at least 3 or 4 vertices. From there, at those vertices you find the value of objective function and get the optimal solution. Clear? This is graphical method of solution of problem in 2 variables. We will be working on it first, then I will definitely explain isocost or isoprofit line problem. Okay? Let us solve this one by corner point method. Isoprofit method I will tell. Isoprofit method also I will tell you. But let us solve it by using the corner point method first. Maximize z equal to 3x plus 4y. This is the problem here. Just use different ink for this. This is the problem here. Okay? Solution you will think later. First you know the problem. Solve the following LPP graphically. First check whether all the parts of linear programming is given over there or not. That objective function z you recognize, it is given and subject to these conditions. Those decision variables x and y, they satisfy these 4 constants. This is 1, this is 1, this is greater than or equal to 0, this is greater than or equal to 0. So how to solve it graphically? Let me explain step by step. At first we will be plotting those constants in equations as equations. See the step 1. Plot the lines on the graph. Everyone knows how to plot it, isn't it? Then identify the feasible region and corner points. Whenever you have plotted, you have got the region which is where the maximum value or minimum value of the objective function will lie, and that will lie at the corner points. Evaluate z at each corner point, then optimal solution at the point where z maximized can be found. These steps I am going to follow, but I will be drawing it roughly now. Okay? Just a minute. Just a minute. I will solve it in this part, that's why we will remove these marks. So what is the step 1 here? This is our linear programming problem. Step 1 is, try to remember, we are going to plot x plus y equal to 5, which is nothing but x by 5, y by 5 1, then 2x plus y equal to 6, nothing but, and y by 6 equal to 1, or x by 3, y by 6 equal to 1. Now what you have to do? Now we have to plot the graph of linear inequation. Being a class 12 students, you must have done it in class 11, but I will remind you. Don't worry. this line is in intercept form. The point 5 sit there, 1, 2, 3, 4, 5, 6. Here also 2, 3, 4, 5, 6. First one, x by 5, y by 5. So this point is 5, 0. You will be practicing with your graph paper. This is 0, 5 and the line is plotted, AB, representing this equation. But you have plotted the graph of inequation. So region will be either directed towards origin or away from it. If you take the help of 0, 0. If you put x0, y0, what do you get? This is obviously less than 5. So the region will contain origin. That's why we will be taking directed lines this manner. Actually this line continue this way also, but I did not take, because from this non-negativity condition it is obvious that solution lies in first quadrant. Solution in LPP always lie in the first quadrant, never in other quadrant. Okay, solution lies in the first quadrant only. Alright, so it will be directed towards origin. Next one, x by 3 and y by 6. This one is 3, 0. This point B. 3, 0 and 0, 6. No, B no. This we have to take different. B we have already taken. So you need to take different here. This you take C. And this point is D, 0, 6. Join these 2 points. So CD representing the second equation, better to say, we have done. But these don't represent any region. You are solving linear inequation. Again go by 0, 0 test. Whether 0, 0 satisfies the condition or not. Put x0, y0, it is satisfying. So region will be directed towards the origin due to the second line CD. I hope you have understood. This second line CD, this one, just a minute, I made it bigger. This second line CD representing this region, okay, this region, this one, and first one you have seen those green lines representing. Now just tell me which region is common to them. The feasible region will be common to all the inequations. Why all the inequations? Because 2 more are there. X greater than or equal to 0, y greater than or equal to 0. That solution must lie in the first quadrant, which I told you earlier, solution lie in the first quadrant only. So which region is intersection of this green and yellow lines that you can see from the diagram? This is the region. Check. This is going to be the region. Okay. P. So feasible region containing which points? O, C, P and B. A and D are not included. Did you understand? Feasible region is that. Now, if you find it graphically, then we have to write coordinate of, we have to know coordinate of the point B, but I am not using graph paper. So what to do? I will be just solving mentally and writing here. X is going to be 1 and y is going to be 4. So this point of intersection of AB and CD will give you the point P, and the feasible region is OCPB. Got it? And the theory I told you that the maximum value of the objective function is written over there clearly, z is equal to 3x plus 4y. What is its maximum value in this feasible region? That is determined by using the corner points. What are the corner points? Z at 0. It is 3 into 0, 4 into 0. Value is 0. Z at C. At this point, 3 into 3, 4 into 0, that is 9. Z at P. 3 plus 16, that is 19. And Z at B, that is 0, x0 and y5. So it is 20. Where did you get the minimum value of this objective function? You got minimum value at the point C. So if you are going to maximize the profit, sorry, this was a maximization problem. Let me check. Yeah, so maximum value we have got at the point P. So maximum value of Z occurs at P1, 4. That is when x equal to 1 and y equal to 4. For that, Z max is what? Z max is ZP, which is 19. I have taken the simplest example for you and have solved it completely. Okay? So this way, maximization or minimization. In case of minimization, the problem will be what? Plotting. But in that case, feasible region in most of the cases, here also you can minimize, but you won't. Who want to minimize the profit? For minimization, constraints will be different, so that you get the feasible region unbounded. But maximum value will be occurring at the corner points by this corner point method. Okay? I would like to explain the isoprofit line method also here. Okay? What is that isoprofit line? In linear programming problem, not so important for pure math students, but this method is a must for students of applied mathematics. Don't worry, this is a very easy method which I am going to explain it to you in terms of the problem we have considered. An isoprofit line is a collection of points which designate solution with same value of objective function. By assigning various values to Z, we get different profit lines. Graphically, many such lines can be plotted parallel to each other. I just tell you the steps because otherwise it will take longer time. Understanding is most important here. Steps for isoprofit line I will tell you first. Formulate the given LPP in mathematical form, that is done already for the previous sum. Identify the feasible region and extreme points of the feasible region. Corner point method, what we did, we will identify the corner points. Give some convenient values to Z and draw the line to obtain XY plane. So obtain an XY plane. Now that line is drawn and draw lines parallel to it, many lines. You will be getting a line which intersect the feasible region at one point only, not many. And you are moving away from origin, you will be getting the maximum value over there. Okay? And it is furthest from origin, has at least one point common to the feasible region. Let me explain here. With the sum already I have explained to you. That sum I am doing again for you. Okay? Just let me take it at different place to explain isoprofit line. This is the same problem we are going to do by isoprofit line method. Iso means same. Okay? This Z value we have taken, then whatever value of, we have taken any value, Z equal to 5, 7, whatever, then whatever value of X and Y you take, Z will remain the same. Why? For Z equal to 10, you get 3x plus 4y equal to 10. This is the graph of a straight line, isn't it? This straight line may represent this line, any point on it will satisfy this condition only. Right hand side you always get 10. Okay? So let us do it now by isoprofit line method. Maximize this subject to this. Once more, just will be plotting these two lines. Intercept form, you all remember. I just remind you once again. This one, x by 3, y by 6, 1. X, y. This I have already plotted. So I will be doing it now. This was our A50, B05, like this. And next one 30 and 06, 30, all right. And we have drawn the feasible region this manner. This was the feasible region. Okay? Origin here. Okay? And this point we got as 1, 4. In graph though you will be able to observe it. It's coming 1, 4 only. Okay? Now, I have to get this maximum value of the objective function z equal to 3x plus 4y by using this isoprofit method. I take an arbitrary value of z first. Say I have taken z equal to 12. or whatever you like. Suppose I have taken z equal to 12. Then arbitrary value, you can take 1, 2, 3, whatever, not 0. Huh? So this is x by 4, y by 3, 1. This point 4, 0, and this point E this point is 0, 3. Okay. In isopropy method, we have to take a value of objective function, then you have to plot. We have plotted, taking arbitrary value 12. Then what we are doing, we are moving this line only. Which line? The line CD parallel to itself. If you move parallel to itself, let me make it a bit bigger. Sorry. This line, if you move parallel to itself, you all can see that now D's position is changed. D was the line initially. Now D moved to here, that D dashed, E dashed. And it is intersecting at one point only. That point is P. You get the maximum value over there because it is at maximum distance from origin. Okay? On this objective function, if you put x equal to 3 and y equal to 4, that z will be 3 into 1 plus 4 into 4, 19. Okay? So at which extreme point it intersects, that you need to know, and from there you will be getting the maximum value. This is isoprofit or isocost method to get the maximum or minimum value. So in linear programming, we will be doing all these things. We will formulate the problem, objective function, all those things, and then we will find the maximum value. Let us go back to one of the problem which I have promised to solve here. Okay? Just go through the first problem here. This one we are going to solve now. This one. This problem we are going to solve now. We have formulated the sum, so we can solve it easily. The sum, the restrictions I tell you, I have written in matrix form, because if people ask you this question, write the matrix form of this mixing concept of two chapters, that is justified. We are going to find the maximum profit from there. Let us do. We'll be plotting. What is our first step? we'll be plotting the graphs of equations. So it is 4x plus 3y to 40 number 1. Next one, x by 60 y by 90 equal to 1. Okay, and maximize this thing. So plotting is not very difficult here. Everyone can do it. Do it in proper graph paper. Okay, yeah, but I am doing it here. 60, 80, 20, 40, 60, 80, 100. So simple two lines over there, that x by 60 and a is there, 0, 80, so this is the line, first one, x by 60, y by 81. But this is not equation, this is inequation. The graph will be accordingly. Put x0, y0, this is satisfied. This one satisfied. So region will be directed towards the origin. Okay, done. Then x by 60, y by 90. X by 60, y by 90. This is the point D or C, whatever you take. 0, 90 and the line is this. This time also directed towards origin. Okay. Fortunately or unfortunately, we have got this region as the common region. No point of intersection is there. So the value of z we have to find at 3 points. Z at O, 6 into 0, 5 into 0. Value is 0. No one want to make 0 perfect. Z at A, 6 into 60, 360. And Z at B, that is 5 into 90, 450. Maximum here. So if you get the condition this manner, Z max, you will simply write 450 when x0 and y90. I mean, no unit of first type being manufactured. Only second time is going to be done. Clear? I hope you have understood. Then there is another problem which I will definitely help to solve this thing. Brick manufacturer has 2 depots A and B with stocks 30,000 and 20,000 bricks respectively. He receives an order of what? From 3 builders PQR for 15,000, 20,000, 15,000 respectively. Okay. Cost in rupees of transporting 1,000 bricks. 1,000 bricks. Take care of this. For 1,000 brick A to P, it will take rupees 40. A to Q, it it will take rupees 20. A to R, it is 30. B to P rupees 20, B to Q 60, and B to R rupees 40. Your problem is to minimize the transportation cost. We'll do it, definitely we'll do. But let us take the depots this manner and builders this manner. 3 builders will be taking this way. Okay? So these are A and B, and these are P, Q, R. P require how much? 15,000. Suppose A has given X units, X thousand. Remember, I am telling X thousand. Okay? Or as 1,000 rupees it is given, you assume that requirements as 15, 20 and 15 only, because 1,000 fixed price is given. So if this one X from B, how much available at A? It is available 30. At B, 20. From A to B, X. From B to P, it will be how many? 15 minus X. So total will be 15. For Q, suppose it is Y, then this will be how much? How much it requires? This requires 20. So you must give 20 minus Y from here. And for this one requirement is 15 again. So how much A can give? It is 30 minus X minus Y. So how much this one can give? Because it requires 15 only. So how much it can give? It can give 20 minus sum of these two. Sum of these two, 35 minus X plus Y. So it will be minus 15 plus X plus Y. This one and this one add up to 15. Clear? So understood how I am formulating it? Question is, how should the manufacturer fulfill the order so that keeps the cost of transportation minimum? Formulate and solve. Simple. We are going to formulate. Okay? This time minimization. Minimize J is equal to how much? From A to P, 40x. B to P, 20. Plus for Y, for Q, A to Q 20 and B to Q 60. Okay, because number of units I have written here, you can see that in these brackets number of units are taken. Clear? And this plus, what about this one? A to R 30. And from B to R 40. Clear? So you need to simplify it. Subject to what condition? This is the condition, xy greater than or equal to 0. 15 minus x greater than or equal to 0. 20 minus y greater than or equal to 0. And Understood? So this is linear programming problem now. This you need to solve, and we will solve it. Now let us simplify it. Simplifying, z is going to be, just check, 40 minus 20, 20x, 10x, 40x, 50x, and y, 20y minus 40y minus 30y minus 70y plus 40 minus 30y. Isn't it? And constant 300, 1500, 2400 minus 600. Please check once more. X part, 40 minus 20, 20, 10, no, 40x minus 20x, that is 10x, minus 30x minus 20x, oh my god, this is 40x minus 20x, 20x minus 30x minus 10x plus 40x plus 40y, 30y, sorry. Oh, x and y, 40x, 20x, 10x, 50x, it's correct. And subject to conditions, for this one, x less than equal to 15, second one, y less than equal to 20, and x plus y, also this x and y are greater than equal to 0. So you need to plot the graph of these linear inequations. Won't give you much trouble in graph paper. Here it is 30, 30, 10, 20, 30, 10, 20, 30. So AB is this. This one 30, 0, 0, 30. X less than equal to 15. 15 somewhere like this. So origin satisfying this one. Origin satisfying this one also. Okay. So for both, and y also less than equal to 20. 20 is here. So for them the region going to be this thing, because origin satisfying all. But there is another one, x plus y greater than equal to 15. So 15 is here and 15 is there. So you are getting another one, another line. But this time we have taken AB, this one C, D, this is E and F. But here origin not satisfying, 0 is never greater than 15. So the region going to be away. I hope you have understood now which one is the feasible region. So feasible region contains how many points? This P, Q, R, D and F. P point is what? P point is this one, no? 15. Just a minute. X less than or equal to 15. So we have to shift this one. Extend this, sorry for that. Yeah. 15 is there. Yeah, now it's okay. So region is shifting now. Just a minute. Because I'm doing it without graph, no? P. Q will not be there in the region now. Just P. So P's coordinate is what? This point X coordinate is 15, and then I am putting X equal to 15 there, Y is 15. So this is 15, 15. This one 15, 20. Not required. R. Here Y is 20. So X is 10. Just put it there. In this graph, Y 20 means X 10. So this is 10, 20. Clear? Now objective function is this. Corner point method, if you go, you find J at E, P, R, D and F. So Z at E is how much? E, start from here. 750, 0 and 25, 1800, 750, so 2550. Z at E. Z at P. X 15 and Y 15. 750 minus 450, 320, 100 at P. Z at E. So 20, Z at E is done. Z at E done. Z at R. At R. 10, 20. So 500 minus 600 minus 100, that is 1700. And Z at D, that is 1800 minus 600, 1200. And Z at F, X0 and Y15, 1800 minus 450, 1350. So out of these you got minimum value here, J at D. Clear? This way transportation problem also can be solved. Thank you for staying with me.